Good afternoon. Can everyone hear me and see my screen? There's only 3 of us in here.
Yes, I see it.
Thank you. There's Corbin. Okay, give everybody a few more minutes. Show up. Thanks, Bryson. All right, I'm going to go ahead and get started. There's 8 of us in here. It's 1:03. I'll check back to see if anybody else shows up. But let's go ahead and take a look at our syllabus. Scroll down, watch your eyes. Okay, so we started working with residential spaces and heating with renewables. And then we were working on our space heating chapter 2. And we got quite a bit of the way through it. We need to finish talking about what's in that chapter 2, which is where we're at. So we're in between week 2 and week 3. So this being Monday, we're still in week 2, but I've got stuff up for you guys to be looking at for the next couple projects. So we're going to jump right into some, we're a little bit ahead, I think is what I'm saying. So we're going to jump right into energy auditing, and then we'll talk about project 2, which is an energy auditing project that we'll do at the Energy Center. Okay. So if you click on home, you'll see that last week we started on the space heating calculations in module 2, and we also were working on our project thermal envelope calculator, which I believe almost all of us, if not all of us, got that finished. So that's one reason why we're moving on. You see module 2 is under week 3, because we still have to look at a few more pages in there before we get into the next module. You'll also see that your project 2 is available, and you'll see this midterm pretest. So the midterm pretest isn't due for a while. Let's click on that. Well, I'll have to work on that. Let's see right here. For some reason, that's not taking me to the link that I thought it would. All right, well, maybe that's not available. It should be available under your modules. If we click under this, you'll see your midterm pretest right there. So it is available. That link is just broken for some reason. And so it's just a 60-minute time test over what we've covered on modules 1 and 2. So that isn't due until February 9th. So we don't really need to worry about that yet. I can bring that back up on Wednesday. But it's in there, and I'll have to fix that length, but you'll be able to see what it covers. This is the link that it should take us to right there. Okay. Now, module 2, we were still in the space heating. So I'm going to click on that. And I'm going to bring us down to about page 15, if I can. Yeah, because we were just finishing up with the basement calculations. And so there's so many calculations in this. I wanted to go through just the last few of them with you, just so that you understand what they are. So right now, what we're doing is we're doing heat loss, heat gain calculations, and learning how you do that through walls, through floors, through ceilings, because we need to understand that that's something that happens in our buildings. If we're wanting to build a smart home, if we're wanting to consider a house that has good insulation or doesn't have a lot of conductive heat losses, then that's one thing that's very important to consider as we move forward. So this first formula, the easiest way to look at these formulas is to really look at the examples. So I'll explain the formula, we'll look at the example, and we'll move on, and we only got a couple more of these. The nice thing is, in our thermal load calculator, we already have this as part of it. So you guys are already using it, but we hadn't really covered why. So you have heat loss through basement floors. Previously, we had talked about heat loss through the walls, and you had to do that in a very specialized, calculated way, which was very complicated. Same thing here. This is the formula for basement floors. We're not talking about a slab, even though it says slab there. We're not talking about slab, we're talking about a basement floor. So Q would be the rate of heat loss through the basement floor. A is the area of the floor. And R is the effective value of the slab. And then we have an option of T, where we have the air temperature minus the air temperature outside. They do talk a little bit about if you've got under floor heating, you've got tubing in the floors. We're not going to get into that right now. That's a whole nother ball of wax. But mainly what we end up with is two formulas here. We have one formula, equation 2.6b, this one right here. If the slab in a basement is insulated with at least R3 underside insulation, or use equation 2.6c if the slab is uninsulated. which would be this one. So how does that work? Well, all we have to do is type in the numbers pretty quick. So let's look at an example. Determine the rate of heat loss from an unheated basement floor slab measuring 30 feet by 50 feet. So that's the size of a basement. Now, W stands for the shortest side of the floor slab or the floor basement. So in this case, it's going to be 30 feet. We look at the temperature differential. We're talking about it's 10 degrees outside in the basement, air temperature is 65. So we first need to use this formula here, since we're dealing with an an uninsulated and unheated slab. And then we've got to apply this. So since the slab has no underside insulation, equation 2.6 will be used to calculate the effective total R value, which is what we need to put right in here. So when we were doing ours, we had an R value, RE. RE was the total effective R value of our slab in our single story house, and we had 11 in there. So that goes if you have a slab. This goes if you have a basement. So all they're doing is using 2.6C as the formula, taking 14.31. You're like, where is that? Well, let's go back. 2.6C. There you see 14.31 plus these constants. So these are constants that they're giving us. And then it's just simply all we need to know is the shortest length of the floor, which is 30 feet. So they put in the constants, they put in the floor, and they come up with an R value of 47.56. So now they're going to take 47.56 and put it back into this formula here. Okay, I see you, Roberto. So when we work on our heat loss, we got to plug in our formula for our heat loss through the basement floors. So we have an area of 30 times 50. That's from the information that was given, 30 feet by 50 feet. And then we divide that by the effective R value that we just calculated of a no insulation under our basement floor, with a temperature differential of 65 degrees in the basement minus 10 degrees outside. And that simply tells you how many BTUs you're losing through your floor. Any questions on how you do basement through floors? Now, right now, I'm not having us do any of these calculations on your homework or your test. So if that takes a little pressure off of you, that should help. Our goal is to just go through this and make sure that we reviewed the gist of it. And we understand that we can't just look at a building and figure out how to call it a smart home, or look at a building and ignore our heat loss and our heat gain. We want to know, how is that done? How can we do that? As you can see, it's a lot of math. Now we are going to switch to the same deal, but now we're dealing with heat loss through slab on grade floors. So this would be if we don't have a basement and we have insulation underneath our slab, and we have insulation also at the corner. So there's two scenarios to be considered here. We have one where we have an uninsulated slab, and then we have another one that has an insulated slab with at least 4 feet of insulation from the edge. So that brings us to two more formulas. Our first formula here is for the uninsulated slab, and it can be estimated using 2.7A, which 2.7A is right here. It's also a fairly easy formula, and It's something that I believe is in our calculator already. So Q is the rate of heat loss through a slab instead of a basement. L is the total exposed length of the floor. So that means we'd have 20 by 25 feet would be our length. Well, it's plus. So 20 plus 25 would be 45, not multiply. So it's total exposed length of floor slab. The difference between the inside temperature for unheated slab and then B if you had a heated slab, which we're not looking at. And then C with the subscript of 0 is dependent upon the type of soil that you have. So you have soil that can be heavy or damp. You can have soil that is heavy or dry, or light or damp, or you can have light or dry soil. So let's look at an example. So determine the rate of heat loss from the shaded portion of the unheated, uninsulated floor slab shown in figure 2.4. The soil outside is classified as heavy and damp. So what we know is it's uninsulated. That means we need to use this formula here. And the soil outside of the slab is heavy and damp. So that means we're going to be using this multiplier here, 1.358. And the inside air temperature difference is 70, and the outside it's 10 degrees Fahrenheit outside. So only two sides of the room slab are exposed to the outside. So the total linear footage of the exposed slab edge is, as we've seen, 20 plus 25, which equals 45 feet. Again, that's 20 plus 25. The value for C is for heavy damp soil. So we see it's 1.358. We substitute that data in. So to find how much we're losing through this slab, an uninsulated slab, there we plug in 1.358 times the exposed edge times the temperature differential, 70 minus 10 degrees outside. And we can see right there, that'll give you your total BTUs. So even though these formulas are not any fun and they look complicated, it's not something that we can't do. They go on to talk about if you have a insulated floor, like you've got water tubing underneath your floor, hot water that heats your floor, then they say it is suggested that the air temperature in equation 2.7a be replaced by a temperature that is 25 degrees higher than room air temperature when estimating the heat loss of the heated slab floor under design load conditions. So that seems like quite the guess there. So I'm not sure how much we want to get into that. So we're not. So we're just moving on, but that's just a note that they gave you in case you're dealing with a heated floor or you wanted a heated floor. Then if the slab is on grade and it is insulated, then we need to take in some other considerations. We got to take in consideration what our R value is between 4 and 16. The heat loss can be determined using 2.7b. So here we have 2.7b. It looks quite a bit more complicated, but it's really not. It's the same formula. We get our length, but now we have to put in more than one multiplier. But before we do that, we've got to also determine what our R value edge is. So that's what our edge stands for. You scroll down, let's look at the example they have. So when you look up here, before I get too far, this time when they have the heavy damp soil, notice on this example, we're going to be using these numbers here. So you'll see 0.755 plus a negative 0.0425 plus 0.0. So we'll plug those in to this formula right here. So determine the rate of heat loss from the shaded portion of the unheated floor slab shown here. We're assuming that we have 2 inches of extruded polystyrene insulation that has been placed at the edge of the slab. It is under the outer 4 feet of the slab. The soil outside of the slab remains classified as heavy and damp. So heavy and damp means we use these multipliers here. The inside air temperature is 70 degrees, and like usual, the outside air temperature is 10 degrees. So what they had to do to find, they have to look up extruded polystyrene insulation. What's the R value per inch? So the R value per inch, once they look that up, is 5.4. This is where they come up with their 2.8 or their 10.8 numbers. So they take 2 inches times the R value per inch. So now we have our 10.8. Now we got to substitute in our values of B subscript 0, B subscript 1, and B subscript 2 for heavy damp soil. So we still have our length. So when we scroll back up here, it's telling us to do our length. Our length is still going to be 45 because we're looking at the same slab. Then we have the temperature differential will be 60 minus 10. We do those first, and then we have to plug in the rest of these multipliers. So there you can see our slab length, our temperature differential, the first constant plus the second constant times the R edge. So you can see right there our edge, which we calculated at 10.8, plus B2 of the R edge of 10.8 there as well. But that is squared. So when they do that, they calculate this out. It's really, again, like you say, a plug-in type number. And they end up with a loss of 1,196 BTUs an hour through a slab instead of a basement. So again, we're not going to have like a test question with this on because these are just too complicated. You got to look up a lot of stuff, and we'd be having to practice this stuff quite a bit. But we wanted to review it to say that we did it and we covered it. Any questions so far or comments? I don't blame you. That stuff's not fun. But you're learning what all goes into a building, all the things that you have to consider when you're thinking about the performance, the efficiency performance of a building or a smart home. Next sections start to get a lot lighter, and we're going to go through them a little bit faster because there's not quite as much stuff in there that we're going to really need to think about too deeply. And plus, some of the stuff gets back into hydronics, and we're not learning hydronics right now. And that'll be the end of this book that we're using of this chapter, and we're going to move on to a new book, a new section. So really all we need to understand here is R values and U values. So if we have an R value, if we know the U value, which you're going to know the U value because manufacturers are the ones who determine the U value. So you just have to determine what type of window you have. Yeah, we're not going to learn this calculation here because you can easily find the U value. And the R value of a window is the reciprocal of the U value. So if you know the U value, all you have to do is take 1 divided by the U value, and you've converted the U value into an R value. And now we can add it to all the rest of our R values. So the unit U value number can be thought of as the effective U value of the unit, or the same thing as the effective R value. That's pretty easy. If you don't know the window, then all of a sudden you're just going to have to guess what type of window it is and get it close. Is it double pane, single pane? and what are the average on those types of windows U values based on the size of the window. Thermal envelope building. This is where we're a little bit ahead of this chapter because we did that calculator and we talked about the walls at length when we were in class on Wednesday. One can also envision each room in a building as a compartment. The thermal envelope of that compartment would consist of all surfaces that separate heated space from unheated space. So we can see in this drawing any of the exterior walls. See, this is unheated space, even in the attic. The attic is unheated space. So we've got a vaulted ceiling. We've got something where we've got to go all the way to the vaulted ceiling and count it as a wall. And in this room, though, we have a ceiling that goes to an attic. So we're counting the ceiling itself. So you can see where we're counting all of the thermal envelope shown. Questions, comments? Okay. The next section is talking about infiltration heat loss. Infiltration heat loss is different than conduction losses. Conduction losses are the losses of heat or heat gain that we get through our thermal envelope, our walls, our ceilings, our floors. Infiltration heat loss is the air that leaks into our building. When we have to determine how leaky of a building do we have. Do we have a building that is tight or loose or average is really what we're talking about. So there's a couple definitions in here, and we call this the air change method of estimating infiltration heat loss. So if we don't have a blower door, we can use this method to determine our infiltration heat loss, which should get you fairly close. Some buildings, you can't really get a reading with the blower door because it is so loose. It has got cracks everywhere and you can't pressurize the building. So when you have that case, then you're going to assume that you're dealing with a very loose building and you're going to have to do the calculations separately. Okay, so a tight building shows all structure joints and cracks are sealed with meticulous workmanship. This is ENRG star rated houses, buildings that have brand new windows that are 0.25 cubic foot per minute per crack at 25-mile-an-hour wind speeds. All exhaust fans are equipped with backdraft dampers, that type of thing. When we look at our chart, let me note, one is for the single-story building, and you'll notice that you've got the square footage running across the top. So we can go from a 900 or less square foot single-story building all the way up to a 3,000 or more square foot building. When it's tight, you would use these multipliers. When it's average, you would use these. When it's loose, you these. And it's nice, you even got a semi-tight in-between number there to help you. Same thing with a two-story building. We have 900 or less square feet. We would use these multipliers. So let's look at some of the definitions. So semi-tight is just between average and tight. Average is just going to be an average house, fairly new, average craftsmanship. You can verify that the windows are decent windows. But if you can't, then then you're going to have to start leaning towards more of a semi-loose type house, or a loose house is it's an old house. There's little or no effort to seal the joints or cracks in the buildings. You can see that it's got no weather stripping around the doors. The caulking is old. The windows are single pane, something along those lines. So it gives you a nice list of things to look for. So what are the kinds of things you look for to help you identify what type of building you have? So if you have visible cracks around the windows and doors, do you have continuous spray foam insulation versus batt insulation? Spray foam would be better. You have poorly installed or maintained weather stripping on doors and windows. Slight air motion detected near electrical fixtures. Smoke that disappears upward into the ceiling. That means the lighting have leaks around them into the ceiling. That would be if you were using like an incense or a smoke pencil. Smoke pencil is similar. We'll talk about that a little bit later. Smoke pencil is similar to how little train engines work. They have a little oil that they put in there, and a little train engine will make a little bit of smoke. That's basically what a smoke pencil is. You pull the trigger and smoke comes out. Deterioration of paint on the downside of the building. Poor quality duct system design. You have interior humidity levels. So if you have a really dry building, generally that means there's more air leakage. I found that interesting. You don't have any fuel dampers on your fireplaces. If you're in a windy area instead of a sheltered building, storm doors are there to help. That might be there to reduce some of the air infiltration. What type of fireplace do you have? Is it old? Does it have cracks around the fireplace? Is it got cracks around the brick? Awnings can help, but you get the idea. You're trying to find a way to classify if this building is a building that you can consider average, tight, or loose in the air infiltration. If you have a blower door, we're going to watch a video on how to do an energy audit at the end of this. A blower door is an example of where you can see a blower door right here. And we have one of these blower doors where we put a big fan in a door and we pressurize the system. So this is basically what it is. The overall air tightness of the building is determined by increasing the fan speed until the differential pressure reaches 50 pascals. Pascals is like PSI, if you don't know. It's just like meters versus inches, pascals versus PSI. So these are measured in pascals, which is approximately 0.2 inches of water column pressure, blah, 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 right? So your fancy number is 50 pascals. The Energy Center, we can't even get it to do it because it's such an old leaky building, as you can imagine. So we can put a blower door in, but we can't get a good reading. Next equation. So one more definition here. If you want to have an Energy Star certified house, requires an air leakage rate of less than 4 air changes per house at 50 pascals. An ultra tight house built to the German passive Haus standard must have a tested air leakage rate not exceeding 0.6 air exchanges per hour at 50 pascals. So if you remember when we were doing our thermal calculator, we put 0.5 in there. So let's look at an example on how you would do air leakage. So this is QI. QI is estimate of heat loss due to air infiltration. N is the number of air changes per hour estimated based on the air seal quality. So that's going back to our charts where we were looking at it at whether it was tight, loose, or semi-tight, single story or two-story building. The volume of the building of the heated space. And then the differential between the outside air and inside air. So it's got a multiplier here at the front as well, 0.018. So let's let's see how you would do that. So determine the rate of heat loss by air infiltration for a 30-foot by 56-foot single-story building with an 8-foot ceiling height and an average air quality ceiling. So because it has an average air quality ceiling, we're going to go all the way back up here. And our floor area is going to be 30 times 56. So we've got 1,600 square foot house, basically. So we slide all the way back up here, and we're looking at our single story building of an average number right around here. That's where they're getting their air infiltration number. So now they take the multiplier times the air infiltration number that we just saw at 0.38, and then we multiply that times the volume. So that's going to be 30 times 56 times the height of the ceiling, which is 8, times the temperature differential, and that'll tell you how many BTUs an hour you're losing from air infiltration. So if you don't have a blower door, this is how you do it. Any questions on this? The next section of stuff is actually things that we've already done. We've had some success. You guys were working on your calculator. As you read through this, you'll see how that calculator was put together and built. So when we did our project 1, we got right down to it and we started putting in all our numbers, and you guys were able to do that quite quickly. You can see our air infiltration number of 0.5 and our design temperature. All that is what we used. This is the building that we used in our project 1 example. Actually, I don't think this is not the building. This is the building they have in their example. And so it also brings us to how to do the exposed area of the walls. Now, we've already talked about this. It's still another challenging thing that we're going to have to take a look at. I'm hoping on Wednesday I'll go over this with you guys again to make sure this is clear. But when we're looking at the wall, we've got to determine that we have an exposed ceiling, and then we've got to determine that we have the R value of the wall. How did we come up with all those numbers that was already calculated for you? Simply, what we did is we had to go with the air inside film. Hold on a second, I need to pause for one moment. Sorry about that. We did the air inside film, which was found in our notes. And then we had to look and find, what is our value of drywall? And then between the stud cavities, do we have studs? That's what this whole thing is. So when we don't have studs, we have an R value of 21, but at framing, we have a stud value, R value of 5.5. Most likely this because we're dealing with a 2x6 stud, and you're at about an R value of 1 per inch for wood. They're a little low. So, 5.5 is close to 6. But they got that off of a chart. Then they have plywood sheathing, tie-vac, plastic barrier. You see there's no insulation value for vinyl siding. And then this is the outside film for winter. So that's 0.17 from our notes that we saw in Appendix B. All they're doing is adding these up into 2 different numbers, and then they're plugging them into this formula here. So you can see 23.5 goes here, multiplied by 8. And then you see this 0.15. 0.15 is based on if your wood studs in your wall are 24 on center, you might do a 10% because there's less. If there's 16 on center, you might do 15%. So what that means is it's either going to be between 10 to 15% of your wall or your ceiling is going to be comprised of wood studs. When we look at our ceiling, we see that we do have wood studs in them, but we have to do it a little differently because over each stud, you still have some insulation. So it's not like insulation, then nothing. If it's blown, if it's covering the stud, you would have to take and measure the depth. So this is blown fiberglass. You'd have to measure the depth that it is to the studs cavity, and then you'd have to measure the depth in between. And that's what they do right here. So they're using a bottom air film because of the way the air is blowing in that room towards the ceiling. And then they have drywall. Then they have the insulation at framing. So in between the framing, it's 40, but it's only 28.3 because we are dealing with not as thick of insulation because there's a wood stud there. Then when we go under framing, we see there's 0 value between framing. And then we see there's 3.5 right here. 3.5 means it's like a 2x4. So, you know, for 4 inches, you're getting close to about, you know, 1 R value per inch. So it's a little less than that. It's more like 0.9. And then top air film, depending on how your vents are blowing, and you add all this up and you get a total number. And they plug this back in. And here you can see they use 10%. They use 10% solid framing because these are 24 on center right here and here. So that's how you have to calculate up all this stuff. And that's basically what we did in our thermal calculator. But I wanted to go over how that was done and show that it's mostly just adding up the R value and the air film to those numbers. And you can see the air film don't add a whole lot. Talking 0.61, 0.61 here. We're talking like it's adding 1 R value to it. So, you know, these things are hard to get exact. So that's the best you can do is try to look at it. And then you got to go room by room. So we already know how to do this. We already know how to do converting. So if we have something that's 10 foot, 4 1/4 inches, we need to divide it by 12 like we did. So we can convert that 10 to 10.35. And it's a lot easier to add. So we did a lot of that when we were working on our thermal calculator. And then you would go room by room and total it all up. And so it says rooms need divided by a center line, which we did. And so in their example, you can see where we were typing in our gross wall area, you can see that this is basically what our thermal calculator was doing. Net exterior wall, you got to take the gross wall exterior minus the window and door area. Okay, so this should look very similar to that calculator. So because of that, we know that we want to do computer calculations so we can change our numbers based on our temperature differential. That's just talking about software if you want to buy it. We've already done this. Now we're not going to spend really any time on degree day method. I think we've done enough of this. We need to move on to some other topics here. And I'm sure you're tired of all the equations. If you see a question that covers degree method, it's really going to be the number, by definition, the number of heating degree days that accumulate in a 24-hour period is the difference between 65 degrees Fahrenheit and the average outdoor air temperature during that period. I'm going to speed us up here a little bit. We're not going to be dealing with CD factor at all. It starts to get way too complicated. And I think we've done a good job of trying to learn how to do this without piling on all of these formulas that we have to remember. And then they also go into estimating domestic water heating loads, which there's more than one way to do this. We're getting ready to go into electrical estimations, which is really what I prefer to do. We can't do electrical estimations when we have heat losses or watt losses, same thing, same difference, through a wall, but we can determine what our water heater is using based on our electric bill. We can measure it in different ways. So this is an estimation on domestic water heating loads. And really what you're going to find out is, doesn't matter how you do it. You can punch in a bunch of calculations like they do here. We're not going to do this at all. Okay. But it's going to be based off of occupancies, how often you use your water, how often, how many people are in it. And it gets really complicated just trying to guess how to do all that when we can put a kilowatt meter on their hot water heater and leave it on there for 2 weeks and have a really much better idea of how much power their hot water heater is using instead of going about it this method. Okay. And they don't get into it deep enough. So they just cover a couple pages and then that's it. So that ends our module 2. And this is the thermal calculator example that we did. So that's coming from question number 7. Whew. Any questions? Okay, so that brings us all the way through our module 2. And we've already done, as a group, we worked on our module 3, project 1. So we can put that behind us. There you have the midterm pretest that I've got to fix that link for. But there you can see, if you want to take it, you can click on modules and click right here. It's not due until the 9th. This homework, the space heating calculation, since we're just now finishing up that chapter, that's not due until the 2nd of February. So you want to get that done by Wednesday. Try to finish that up today or tomorrow. And then that's going to bring us into our next section, module 4. Module 4 starts to bring us into an energy auditing outlook. So module 4 has an e-textbook. This is from the old book that we used to use. They haven't upgraded this book in a while, and I haven't found one yet that I think is worth using 100%. So we're going to just sample some of the chapters out of it and use it for the home energy auditing section. Then you have your assignment 3, conducting a home energy audit. It's actually fairly easy, mostly true and false. You should be able to get through that one. This section here is not going to be based on a bunch of calculations, not ones that you can't do easily. There are a few, but They're pretty easy. Then you have, under your learning activity, you have a video that we'll watch on Energy Auditing 101. And I kind of feel like we want to watch that first. That'll get you thinking a little bit more about different things that you can be doing. Then you have a reference on do-it-yourself energy audit. This isn't a requirement for you to do, but it's a good reference worksheet if you want to get a little more into energy auditing. This is a job. So some of you want to be wind techs, some of you want to be solar techs, some of you end up being energy auditors, whether you realize it or not. It's just kind of the way things go. So this is just another area of work that you can get into. And there's a variety of energy auditing jobs. There's ones that are very simple, where you're just doing some insulation checks and you're just caulking windows. Then there's new construction. Then there's doing full-blown buildings with blower doors. It all depends on who we're talking about and what the situation is. So there's different types of jobs out there. A lot of utilities have positions open also for energy auditors. So if you're looking at doing energy auditing, you might look at Duke Energy, where they'll send people out to do energy audits at people's homes. Other states, they may do something where you have to be a BPI certified energy auditor. And that is something that you can get. You can take that test. We don't do that because BPI certification isn't required in Indiana. But if you were to maybe go to another state, it might be, and it's tough, it's hard. This is just serving as an introduction to it. And if it might be a pathway you go down, get a job, and then possibly they'll send you off to get your BPI certification so you don't have to pay for that. So before we get into too much of this, let's watch a short video on how to conduct an energy audit. Here's your homework. Okay.
Hi, it's Don Kennedy with ProMaster Home Repair and Handyman of Cincinnati. I'm so excited about today's video because I get a lot of questions from viewers and folks that come to our website about energy efficiency and how to improve their home and make it more energy efficient. And so today, I've asked my friend Tim Courtier, who's the owner of Pro Energy Consultants, if we could tag along on a real home energy audit. So let me introduce you to my friend Tim, and he's going to tell you all about what we're going to do.
Hey, Don.
Hey, Tim, I appreciate you
Thanks for
letting us tag
having me.
along
No
with
problem.
you today.
No problem at
First of
all.
all, I mean, tell me a little bit, a lot of folks today are getting home energy audits,
Mhm.
so they kind of get a report
Right.
to understand, how they can improve their home and make it more energy efficient. So a lot of times the people will call the power company and the power company guy will come out, tell me how you're different. What do you do?
Well, we take a different approach than the power company does. Now, when the power company comes out, they're not going to use the infrared cameras that we use, and they're not going to put the house under a negative pressure to find where all the air leaks are as well. They're going to come out and tell you to buy Energy Star appliances, and they're going to tell you to put CFL light bulbs in, and that's about it. We get a little bit deeper involved in that. Like I said, we do an infrared scan to where we can find any missing insulation or lack thereof. We do the negative pressure test to where we can see where there's any type of air infiltration in the home itself. And then we also test the ductwork itself to make sure that you're getting the proper amount of heat or air conditioning to those rooms. So we find out where you're losing energy and why, and we can make your home more comfortable.
Well, that makes a lot of sense because, I get calls from folks all the time like, hey,
Sure.
should I spend this $5,000 or $10,000 on
Sure.
new windows?
Sure.
Or this guy quoted me $2,000 for new insulation,
Mhm.
or should I, spend the $12,000 on a new
Right.
heating system? So people are just throwing good money after bad in an attempt to try to make their home more efficient. You say you shouldn't do that without getting an energy audit first. Right? Why
No.
is that?
Get the energy audit first. Our motto is we don't guess. We find out where you're losing the energy and why. And then we also give you a detailed report of where you need to focus on investing your money to where you're going to get that return on your investment.
Okay, I see. So then you could then take the report and either do that work yourself
A
or
lot of
hire a company like ours to come in and do that and
Sure.
actually focus your dollars towards where they're going to make the most impact.
Exactly.
Okay, that makes sense. Well, now my only next question is first, let's talk about some of the tools. So maybe you can kind of give us a tour of some of the equipment because we like tools in our business. We think that's cool. So show us some of the equipment you use and maybe then we'll take a
Sure.
look at how we go about doing it.
Sure, sounds good.
Let's go.
All right.
All right, we're inside now where it's nice and warm, but I've been watching Tim starting to set up. And the first thing I notice is this large red contraption. What, are we going camping, Tim, or what is this?
Well, what this is what we call a blower door. And what we use this for is this puts the house under a negative pressure. Basically what that means is it's simulating a 10-mile-an-hour wind blowing constantly on our four walls of the home. That way we can see where there's any type of air leakage in the home, be it from the windows, the doors, basically the entire building envelope itself.
Okay.
And that tool that you're
Yeah,
holding in your hand there,
what is this here?
this is what's called a digital multimeter. And what we use that for is once we're done doing our blower door test, is we can figure out actually the approximate size leakage that's in the home itself. So we can actually tell you how big of a, in essence, a hole is in your home.
Cool.
Very cool.
Let's crank it up.
What we're doing now is we're using a thermal camera, and this is actually showing us where you have that cold air coming in. The blue here is showing us the cold, and as I come forward here with my smoke pencil and shoot the smoke in here, you can see the smoke coming back at us. So you can tell that there's a lot of air from the outside coming in. Not only is it coming in from the flue itself, as we come to the side here, you can see these gaps along the masonry, and as we shoot it with the smoke, you can see how it's just shooting right back at us. And also with our thermal camera, we can see those temperature variations. And obviously they have 40-degree air coming in, which is not a good thing. The thing is, like this particular customer, they just had new windows installed. And a lot of times what you find is people don't need new windows. That's what I'm finding here is they actually have a lot of air leakage around the windows themselves. When I shoot it with my infrared, I can see the cold air coming in. And then we use our smoke pencil to where you can see all that air is blowing that smoke away. This is a simple repair versus actually just replacing your windows. You can shoot the color to seal that on up.
It's kind of like an investigator. We've been watching him as he's kind of snooping around the house here with his infrared camera. You found something really interesting under this window. What's going on?
Well, again, this is a brand new window that they installed.
Brand new window.
Brand new
Brand new
window.
window. Okay.
What we found here is there's air leakage underneath the window itself along the trim here. So again, all we need to do is just lay a simple bead of caulk, and it'll take care of that air leak. You won't have those full drafts.
So this is really an installation in window. All these times people spend so much money on new windows
Correct.
and they're not getting the performance of it simply because due to a deficiency in the installation.
Correct. Yeah, a lot of the times when they install brand new windows, they neglect to seal around the window itself and around the trim here, which more often than not is where you're going to get your air infiltration.
Tim, what about doors? I mean, tell me what you're looking for.
The doors are a very important area to check for air leaks as well. And as you can see on the thermal camera here, we have 33-degree air coming in underneath the door. And then as I pan up here, you can also see a lot of air coming in along the sides as well. And again, as I shoot it with my smoke pencil here, you can see all that air that's coming in, just blowing all the smoke around here. Now, in this particular case, what we need to do is replace the weather stripping around the door itself. And also on the trim area here, once again, it just needs some simple caulk to seal that air leak up, and you're good to go.
That's a beautiful old hardwood door. We definitely don't want to replace that.
Now we're in the basement, and one particular area that you really want to focus on is what's called the band joist or the rim joist. And what we found here is someone has insulated the band joist, but as I shoot with my camera here, there's actually low 30-degree air coming in through that insulation. And if you look up inside there, it's starting to actually blacken the insulation because it's basically acting like a filter at this point. So typically what we always recommend you have done, instead of the insulation such as this, we recommend using the foam insulation where you're going to get an air barrier to stop that air from coming in, as well as a thermal barrier at the same time.
Here's a close-up of what Tim's talking about. You can see the gaps that are between what's called the sill plate and the band board, or sometimes called the rim joist. And air is just flowing right in there. And it doesn't matter if your home is new or old. In fact, when I moved into my place, new home about 3-4 years ago, I had to take some foam and seal up all of those gaps because the contractors aren't going to take time to do that.
And now we're in the attic space, which is a very important area and also a very neglected area, as we can see here in this attic space. Now, if you actually look down inside here, how the insulation itself is actually starting to blacken. Now, once again, they didn't install baffles in there, so the insulation itself is covering up those soffit vents. And again, it's acting like a filter. So what we actually need to do here is to install baffles to where it's going to open up to those soffit vents to get the proper air ventilation through here. And then we also need to add an additional amount of insulation in here. Now, they've actually floored in here, so we have a maximum of about 6 inches of insulation in this attic space. Now, in this area that we're in, you actually want to be at around an R49 value. So we're going to need to add about 12 to 15 inches. And now as I'm scanning the ceiling here on the second story, I'm actually finding these areas of very cold spots where we're actually getting down low 50s, high 40-degree mark. And again, with that lack of insulation in the attic space, that's giving you all these cold spots, which just again shows us why we need to add that additional amount of insulation to the attic space. Another thing that we always want to check, especially on a second story with attic space above, is any type of penetration that's going into this attic space. So we have a light here, and I'm actually checking it, and this one's good. It's sealed up. There's no air coming in through there, but that's a real common source for having that unconditioned cold air from the attic space come in to the living space here in the bed. Now, again, we're on the second story, and as I'm scanning this closet space in here, I find there's a lot of cracks in the plaster through here. And if I shoot it with my thermal camera, I'm getting some real cold temperatures coming out through there. And we can actually feel a draft coming through this closet itself. So what we need to do here is, again, we need to seal those cracks up to prevent all that air infiltration of coming into the living condition space.
Added benefit of having a professional energy auditor conduct an energy audit versus maybe just somebody from the power company is that a gentleman like Tim has a lot more knowledge about appropriate residential construction techniques, and can spot problems, not only that affect the energy performance, but that could be other safety problems in your home. And that actually happened while we were out at this home. While we were down in the basement, Tim spotted something that actually could be a serious safety concern. It could actually kill the occupants of the home. So Tim, why don't you explain what you found?
Well, what we found here, Don, is I was looking around, I actually saw the chimney for, this is a gas water heater.
Right.
So obviously it uses combustible gas. And you actually have to vent those gases outside of the home. And like you said, this is a serious safety issue. It can cause serious illness or even death. And as you can see here, this pipe is actually disconnected from the water heater itself. So you have those harmful carbon monoxide gases actually inside the home itself.
Now, this family did not have a carbon monoxide detector. I would hate to have seen one. I almost don't want to know, but if you don't have a carbon monoxide detector, please buy one. I have one on every level of my home, and it would tell you if something like this was occurring that was spewing carbon monoxide into your air. Well, Tim, we started here at the front door. We're now done. Back at the front door. Maybe kind of give us an overview of what we did here today.
Well, basically, what we do from here is, after I take all my findings within a 48-hour period, I actually build my customers a prioritized action plan. And what that action plan is what we recommend they do to improve their home, to make it more energy efficient, and where they're going to save the most money. And basically, like I was telling you with my multimeter here, I can actually, with the findings that I have, in essence, tell you how big of a hole that you have in your home. Basically, how much air infiltration is coming into your home and how we can improve that. And that's all in the report for the customer. And any customer, if they need someone like you, such as yourself, we make those recommendations. And a lot of the things that we do find, as you've seen, is simple things that customers themselves can do to improve their home and make it more energy efficient, not have to spend the extra money to have that taken care of.
Well, great. I look forward to the report, and thank you so much for
Thank
letting
you,
us
Don.
tag along.
No
This was
problem.
a learning experience for me. I hope you at home enjoyed this and learned something from it. Thanks for watching.
Okay, so that was a nice little video on some of the stuff that we're going to be trying to do when we get into energy audits at the Energy Center. Was there any questions or comments over that video that we just went through?
Are we going to be messing with some thermal cameras?
Yes.
That's what I'm talking about.
Yeah. HVAC has a thermal camera. I generally borrow a thermal camera from HVAC, and then I let you guys go around the building and start looking at stuff. So yeah, that's on our list. Good question. Okay, so chapter 4, conducting a home energy audit. So this will go fairly quickly. I'm just going to highlight the areas, not read it, the whole 28 pages to you, but I'm going to show you where you need to focus and what the chapter is about. So one thing that we want to talk about right away is creating an electrical chart. So what we've done is we've done BTU calculations, but we don't know how much energy is being used by the actual occupants of the house. So that would deal with all the appliances, all the stuff that you have to go through. And so that would be done on a room by room basis. So in order to do that, you would need to go, say, into the kitchen. If you're in the kitchen, you might see a stove, a blender, a mixer, a refrigerator, a dishwasher, and you have to find out how much power you are using per appliance. And you could also look at somebody's electrical bill and just say, well, you use this much power. That's one way to do it. But if you're doing an energy audit, what you're trying to do is look at all of the different loads in the different rooms and calculate them individually to get a better idea of where the waste is. So lighting used to be a much bigger issue than it is today, because we now use LEDs and CFLs in most of our homes, unless you're still using incandescents. If you're using incandescents, then about 25% of your bill is from lighting. If you've shifted down to LEDs or CFLs, you're down closer to 10%. It all, again, depends on the occupancy and the person. So if you were to go into the Energy Center, or if you were to go into your own home or your own room, and you were to look at the room lights, you need to count them. So let's think about the lights in the classroom. There's quite a bit of light bulbs in those lights that we use. So you would, one, have to go, okay, I've got maybe 10 lights. Does each light have 2 bulbs or 3 bulbs? Those types of fluorescent lights are usually about 32 watts a bulb. And so you'd have to go, okay, and those are going to be on for maybe 4 hours a day, or, 8 hours a day, and then calculate your total watts.
Did
So
that
there,
go
go ahead.
The those long fluorescent lights?
Yes. What about those?
How much do those do?
Those are usually about 32 watts each.
Okay.
It depends on the size of the bulb. It really does. So the easiest way is to look at the light bulb. We have a pretty cool little lighting trainer that we'll pull out on Wednesday, and we'll look at, and it can show you some of the differences between the bulbs and the power that they use. And it helps you see a little bit more of people's usage patterns. So some people leave their lights on all the time. leave things on all the time, they don't realize how much energy they could be saving if they're turning these things off. Once you do the calculations, then you start to see that. One of the easier ways to measure power consumption is if we use something like a watt meter or a kilowatt meter. So you can buy these. There's different types out there. Most of the time, they're going to be just 120, where you plug them into the outlet and then you plug your device into the watt meter and you turn your device on. So once you do that, then you're going to see real time how many watts that device is really pulling. So we have several kilowatt meters at the ENRG Center that we can use. And what's nice is they can do it immediately, or they can do it over a lengthy period of time. So if you want to measure over a month, you can program it to measure how many watts it's using over a month. You can also program into it about how much it is per kilowatt. So maybe like 11 cents. Program all that in there, and then this thing can give you a really accurate number on exactly how much power this device is using. So that gives you a list of some of the different things that the different meters can do. And you can buy these meters at Menards. They're not real expensive. Well, things have gotten more expensive, so I'm not sure anymore. But usually they're around the $20 range. Okay. So we know that with a blender like this, you're not going to use it all the time, but there are certain types of devices that still pull power when they're plugged in. So if you plug this blender in, it might be pulling 287 watts when the blender is running, but most likely it doesn't pull hardly anything at all when it's sitting there. But some devices like computers, alarm clocks, different things you don't really think about, we call those phantom loads. So you just want to see what they are doing when they're at rest and what they're doing when they're running. So are they in sleep mode is what we're talking about. To measure the power use for a refrigerator, freezer, or other large appliances that operate in cycles, things like a dishwasher or a washing machine, you know, most of the time it's a little easier to get a different type of equipment that you can put on your inside your electrical panel and measure the total wattage being pulled by that device over the wires, which we have those at the ENRG Center. We have a couple different systems that will show you that you could use that can keep track of your usage all the time. And that's becoming more and more common. They're getting cheaper. So we know that we can't always do that. It says you will not be able to easily measure the power of some electric appliances because they operate on a 240 volt power source, which most power meters cannot monitor because they are hardwired into the home's electrical system. So if the system's hardwired or plugged in, you'd have to make sure that you had a 240 volt kilowatt meter as well. I don't have one of those, but they do make them. But that's where I start to say a clamp-on electrical meter can do the job too in your electrical panel. So when you're looking at a system like this, you've got several different pieces. This is our computer. We've got a printer. How often do you use the printer? If you use the printer like once a month, you probably don't even want to calculate it. If you're using the printer like all day long, then yeah, you're going to want to calculate it. If you're using the scanner hardly ever, but the scanner's plugged in all the time, it may have a phantom load on it that might be 30, 50, 100 watts. That adds up to dollars. So if someone's trying to reduce their electric bill from $150 to $100 a month, and you're trying to help them maybe put a solar system on their house of a certain size that could maybe make $100 a month worth of electricity, but not 200 or 150 because they can't afford it. This is where you start to look at, okay, what devices do I need to unplug? What things do I use and what things do I not use? What things are plugged in all the time? So in order to measure this, you'd have to measure each one of those devices individually. Another way of doing it, if you don't have a device like a washing machine or a dryer, might plug into a wall outlet. It won't be as accurate because these things have cycles, but you can see on there how many amps it pulls when it's running, say on its rated speed. So this washing machine, when it's running at its rated capacity, it's pulling 10 amps at 120 volts. So we take 10 amps times 120 amps times volts, and we would get watts. That would tell us that we're getting 1,200 watts that this washing machine is using. So that's what the next section is talking about. It's talking about taking volts. If you want to find volts, you use Ohm's law. So current or intensity times resistance will equal volts, or E, electromotive force. Same thing with watts. If you take the current times the voltage, you would get the wattage. So that's something I think most of us already know, but that's something that we're a little more used to doing since we've talked about power a lot. This section here just talks about how it's not as accurate just to go off of the nameplate 120 volts times 10 amps because a washing machine has different cycles. So that's where you'd want to measure it with a clamp-on meter or a special type of kilowatt meter that can handle that type of power. So we're still at about 11, 12 cents a kilowatt hour around here in Indiana. So most of the calculations that you'll read in this book are still pretty accurate, to believe it or not. But you can see many different devices have different loads. They give you some examples of an aquarium, a clock radio, sitting there only pulls 10 watts, which is nothing. We're talking pennies on the dollar that costs a person a month. Coffee makers pulling quite a bit of watts, but how often does it run? Is it running for just an hour a day? Then it might not be that bad. A clothes washer, clothes dryer are going to be running a little bit more often, and they may also have they'll have a higher wattage, and it just depends on how often you use it, how many people live in the house versus how many people are washing their clothes. Same with the dishwasher or anything else. You know, each one of these devices pulls different amounts of power, and it all adds up. So if we were to do BTU calculations through the wall, that's not going to tell us any of this stuff. So this is the next step. So I'll move on. These are just examples. Now they go on and talk about if you want to determine how much gas fuel is being used, then in the home, you would simply have to look at your bill. That's really about the easiest way to do it on gas because it's already metered. And so there's really not much you can do except turn your thermostat down or not use your gas stove or your gas dryer if that's what you're using. But it's very difficult to measure gas on an individual appliance. So you would want to see what your monthly bill is and how much gas you're using. And that's one of the problems with gas is solar panels don't replace gas, but they do replace electric heat. electric stoves, electric dryers. So gas is going to be measured in decatherms. Same thing, they go on talking about if you've got a house that's heated with oil or coal or other fuel, they go on to say there's not really much of a way to determine these except looking at their fuel bills. So how much coal are they buying? How much wood are they using? How much oil are they buying is going to give you basically all the information that you can do with it. This will just tell you that you're spending this much money on this type of heating system. And you could do a full energy audit and try to determine where their BTU losses are, and you could determine if their furnace is too small when it comes to replacing the BTUs they lose through their walls, their ceilings, and their floors. Again, electric bills go a long way. We can find out a lot of information by just looking at someone's electric bill. So what we want to do is conduct an energy loss audit, or how much energy we're losing through heat transfer. So this is really an energy audit. It's determining the air leaks in the house. So this is basically what that gentleman did in the video. This is what the rest of the chapter is talking about. It points out things that you want to look for. Air leaks around electrical outlets, switch plates, as we've seen in the video, around the window frames, around your baseboards, things that are hidden. You can use a smoke pencil like he did, or you can feel it with your own hand, use an infrared camera or a thermal type camera. It doesn't have to be infrared imaging to find the temperature. There's plenty of $20 thermal cameras that'll tell you what the temperature of that air is. Thermal just kind of helps you pinpoint it. Hatches in the attic, fireplaces, weather stripping around doors, things that we are aware of. And this goes and talks about conducting a pressurization test. We've already talked about a couple different ways of doing air infiltration. We have our formula that we learned in chapter 2 from our space heating. Then we also learned a little bit more about how to do that if we had a blower door in our house. We need to really have a blower door to be able to do that. And it's really cold outside. So doing a blower door on Wednesday is not something I think we're going to be doing. Here's where you can see that you could use a smoke pencil or an incense stick. Incense might be something that aggravates people's nose. They don't want to smell it, but an incense is pretty safe. You light it, it makes smoke. Put it around the windows, put it around the doors. Anywhere where you might find a leak. And we're not only talking about leaks in the doorways, we're talking about leaks around the fireplaces, around the cracks on the fireplaces, and outside. So when we go to the outside of the building, we have penetrations that come into the building, such as pipes, conduit. Are they sealed, or was a hole just drilled through the brick and a pipe stuck in there? Because now all this air is blowing through this hole. So that should be sealed up. There you can see on the outside of the windows, you can see where the caulking has cracked. So we look a lot of the inside of the stuff, but don't forget about the outside. So all exterior corners where siding and chimneys meet, window casings where they join to brick or siding, door jambs where they meet the exterior walls, areas of the foundation, lower areas. We saw some of that stuff in the basement when we were watching that video. Then they go in to talk about how to determine heat loss through walls and ceilings. They talk mainly about using a thermal camera. Thermal camera in this case is black areas are for cooler areas, white areas are for warm regions. So you can do a thermal camera in black and white, and they can show you a lot of different things. So if we were to go outside and use our thermal camera on this house, any area that's black is showing up as a colder area than something that's white. When we look at this wall here, we can see this wall right here is white. That means it's got good insulation in between the studs. This right here has some insulation. This right here has no insulation for some reason. You can even see the wood studs right here where you can see the black lines. They're cooler. They have less of an R value. So that's one use of the thermal imager. This also talks about insulation, and it gives you some more information on types of insulation that you need in your home. So in your homework, you have a couple definitions. And so you'll find some of the definitions here. You'll find some of the definitions at the end of the chapter. So rolls and bats versus foam versus blown fibers. That's one of the problems with blown insulation is it falls down over time into the wall. And so only half the wall may be insulated where the top half, it needs more insulation blown into it. It just compresses over time. We've already looked at this map before. We said that we were a 5. This takes it a little bit further and shows, you know, you just got to find a chart here. So if we're 5 and we have an electric heat, then they recommend R38 to R60 insulation. And like I said, that's going to be about like 18 to 21 inches of insulation. In that house that he was looking at, he said there was only 6 inches because they put the floor in there. So it's not going to be as well insulated as if it were properly insulated with much thicker insulation covering the top of the studs. So just in between the studs is only going to give you 4 or 6 inches of insulation, and that's not going to get you up to your R50. Same thing you can see with gas. You can see in the wall cavities, you want around R15, R21 insulation if you're a number 5 in our area. These charts here are just giving you a quick look of what is the average R value per inch of thickness for, say, fiberglass or fiber blown insulation. So if you're trying to find some of that information, here's another chart for you. So we were looking at extruded polystyrene before when we were at chapter 2. They were at 5.4. They're saying this is about 5. So you can see it's about the same. Hardwood flooring, wood 0.9. It's about where we're at. It's about an R value almost of 1 per inch. They go on to talk about if you don't know how to check if you've got insulation, then you need to maybe remove a light switch cover and see if you can look inside the wall. Carefully remove a outlet cover, something like that, and poke around carefully to see if you can see that there's actually insulation in between the studs. That's not the best way. Another way is like we saw at the ENRG Center is to drill a hole in the wall and actually look in the wall to see if there is any insulation in the wall where you can blow it, or you can you have to take the wall down if you want to put a different kind of insulation besides blown insulation. Spray foam would work. You could spray through a hole Energy audit. So now when we're talking about energy audit, it's getting back into what that guy was doing. We're going to make an energy audit report. We're going to do a real simple one, not try to do one that's too complicated. I got some examples for us to look at, to use. We might change those around. I'm open to some different ideas, but you know, these things can be really complicated or really simple. I like simple. So this is where they're just taking pictures. When I bought my house, I had a guy come out and do an energy audit, and it was really simple. He just took pictures like this and showed me some of the bad places. So this is a recessed lighting where his thermal image camera is showing that it needs sealed. Caulking would help. There you can see if you got several recessed lights, every one of those, you have to be careful. You don't want to cover those with insulation. That's usually what the problem is you've got to have a light that can be covered with insulation, or that light has to be sealed. So recessed lights can be very leaky if you got a lot of those. There you're looking at a skylight window, same idea. All those black spaces around there are where we're getting air infiltration. You know, you're looking at 46-degree temperatures versus the temperature inside the house is 65. This is just blowing in 45-degree air. It's like if you had the window open. There you can see in the wall around the switch plate, you might be able to put your hand around the switch plate and feel the cold air blowing. So you might want to put some insulation around this area, or a gasket is usually what they have. A little rubber gasket that'll go around this to help block that air, keep it in the wall. Window cracks, doors, sliding glass doors are really bad. Usually they have a lot of leaks. Anything that moves that's on a track. There they're seeing you don't see any insulation in between these studs here. Or on these steps, there's a lot of cold areas where the framing meets and the wood studs come together. So what we really need is to get our FLIR out and use that. That is it for chapter 4. It's a pretty easy lesson. You have key terms in here. So if you're trying to find definitions, you might want to look in here on this page. Any questions or comments for me? Get your attendance, Roberto, before I forget. Okay. So we've been going about an hour and a half. This is a reference, a do-it-yourself energy audit. It's pretty jam-packed. I'm not going to go through the whole thing. It's mostly a repeat of information, but it's color. It's got some good things to point out in there. So some ideas. It's got pictures of insulation. It's a good resource and a good reference. And this right here is just our blower door manual. I don't expect you to look at it. I just thought if you're curious about this stuff and you want to see how our blower door manual works, I put that in there, but it's about 100 pages long, so I don't expect anybody to read it. But if you're wanting to know, there it is. There's a reference for that. Let's go to modules. So on Wednesday, we'll wrap up with any of our calculations that we needed to do. Make sure everybody has their project 1 done. make sure everybody's doing good on their homework and and has access to this midterm pretest. And then we'll get started on our project 5. So your project 5 is going to look something like this. So we did an energy audit at Logansport. So this is just an example of what some students did. I don't know. Yep, there we go. So this is just a wrap of what we did. We ran out to a building. We didn't have a whole lot of time to do this, but we went around and took pictures of cracks. It counted how many light bulbs they had and estimated how much they're using per hour and estimated how many watts per use. So how much does it cost per hour? 3 cents. You just need to know that. And then how many watts per year, estimate that based on how many hours. And taking some pictures and photographing windows not sealing properly. Lighting in that room, cost per year is $48 a year. They have a lot of lights. But mostly this right here is just to give you an example. They need to insulate around the attic coil. You're going to find all kinds of things at the Energy Center that need fixed. And you just want to document that. And then we'll be able to see how much power we're using. Overall, we did everybody's office. A lot of them had baseboard heaters and individual air conditioning units. Those things were costing them quite a bit of money. Baseboard heat's real inefficient. They had a lot of holes in the wall. Yeah, I wanted to, yep. So this is the idea of what you're going to be working on. And I'll split this up and we'll work individually on some of the different areas and try to find and locate some of these. We'll use our thermal imager. But you can see cracks everywhere. There was nothing we could really do to help them. They needed, the building was just so old. They needed all new walls, new insulation. They needed to seal up around all the cracks and areas. I realized this thing was pretty big. The attic insulation was really bad. They only had a couple of inches of insulation in the attic, as you can see. 2 to 3 inches was all they had. That needs to be like 18 inches. We made some recommendations for them. Lighting, heating load, cooling load, computer load. And their yearly bill was $8,652. That's how much it cost them a year to run that building. And their monthly electric bill was on average about $721. After we did our audit, we were really close. We estimated that they're around $7,536, and their monthly estimated bill was probably around $628. And it's all because of all those loads that we calculated. So obviously it's hard to get it perfect. Can't get it perfect, but we got it pretty close. And that shows you the value that you have when you're working with doing an electrical audit, as well as an energy audit that goes with the conduction losses and the blower door test. So that's what that is. But we'll look at that on Wednesday when we have some more time. But that is all that I have today. So what you guys need to work on is just look at your due dates. You got until February 7th to get assignment 3 done. You could get that done pretty fast today. It's not a hard one. Once you get all that stuff done, then move to your midterm. Okay. There aren't any questions for me. I guess that's all I have today. I'll let you guys go. So if you do have any questions, stick around. If not, it's 2:39. It's almost 3 o'clock. That's good enough for one day. I just wish you guys the best for the rest of the day, and I will see some of you tomorrow evening at 5 o'clock, and the rest of you on Wednesday on campus. Have a good day.
See you, John.
Bye.
Bye-bye.